Hello friends, welcome back to JEE Blunders where you learn the don'ts first. Today I thought we would try a problem that is almost as old as I am, from IIT JEE 1999. And so here's the problem. A cubical block of side A is moving with velocity v on a horizontal smooth plane. So this is the frictionless plane. This is the cubical block of side A moving with constant velocity v. It hits a ridge at point O here. The angular speed of the block after it hits O is, and we have four options: 3v by 4a, 3v by 2a, root 3v by root 2a, and 0. And so, just dimensionally speaking, all of these options could be correct. So we cannot just eliminate any of these just by checking dimensions. So we actually have to solve it. So let's go ahead and try doing that. So common way to approach any mechanics problem is to start off by writing the famous conservation of momentum and conservation of energy equations. So let's start off by doing that, and this is fairly standard for any mechanics problem. So the first thing we want to do is to conserve energy. So that should give us something, that should give us an equation. And we also want to conserve angular momentum. And when I say conserve, I mean, intuitively we know that the block is going to hit the point O and then topple over. I think it's fair to assume that it's going to be in pure rotation about the point O. So we can assume that it's going to be toppling over with this angular speed omega or angular velocity omega about the point O. So yeah, when I say conserve, I mean between the initial state 1 and the final state 2, right? So we can conserve these quantities, energy and angular momentum, between these two states, right? So how do we conserve energy? So the mass is not given to us. Let's assume it has a mass m, which I think very likely will cancel out. So the initial kinetic energy in state 1 should be equal to the final kinetic energy in state 2, right? So the initial energy is just purely translational, so that's just half mp squared. The final kinetic energy, I'm assuming, is purely rotational, so it's going to be half I about the point O, where this is moment of inertia about the point O, times omega squared. So IO, we will have to calculate that, so let's do that. So let's consider right, so we know that the moment of, if this is A, it's cubical, so this face is a square, so we know the moment of inertia about this axis is going to be ma squared by 12, right? And moment of inertia about this axis is also going to be ma squared by 12 by symmetry. So moment of inertia about, let's call this C, is going to be, IC is going to be ma squared by 12 plus ma squared by 12. That's the perpendicular axis theorem. And hopefully this is a good review of those concepts. So that's going to be ma squared by 12 plus ma squared by 12, which is ma squared by 6. But we want to find moment of inertia about one of the corner points. So IO will be IC plus m times the distance, the distance between CO, right? So the length of the diagonal is going to be root 2a, right? This entire length is root 2a, so this length will be, and I'm running out of space here, that length is going to be root 2a by 2, or a by root 2. Sorry, I'm not writing down all the steps to make this to make the drawing a bit neat. So this would be m times a by root 2 squared. So this is the parallel axis theorem, and this, to get IC, we use the perpendicular axis theorem. Okay, and this, so now solving for this, ma squared by 6 plus ma squared by 2, and how much is that? That would be 2 ma squared by 3. So hopefully that me box that properly. Yes. So this is the I moment of inertia about the point O, right? So let's move down a little bit. So that means, half and half is going to cancel out. Mv squared should equal I naught, which is 2ma squared by 3 omega squared, correct? So looks like we are almost there. Omega squared is 3v squared by 2a squared. So omega would be root 3v by root 2a. And it looks like we are done. Oh, wait, this boxing thing didn't work. Okay, that's fine. So root 3v by root 2a. Are we done? Because we just, it looks like just conserving energy was enough to solve the problem. But I'm just curious to know what's going to happen if we conserve angular momentum. Because, technically, about the point O, there is no external torque, right? If this is our system, if this is the body that we are studying, there is going to be no external torque about the point O. So technically the angular momentum in state 1 about the point O should be equal, let me write that down first. So angular momentum in state 1 about the point O. Because when we say angular momentum, we need to specify about which point. So that should be equal to angular momentum in state 2 about the point O. Correct? So let's see what, hopefully it gives us the same answer, but let's just check. So angular momentum about point O in state 1, it's R. So angular momentum is the moment of linear momentum, right? So R cross P. So if this is the position vector, or this is going to look, don't want to miss this diagram, but let's see if I can do this. This is going to be the position vector R, right? R cross V. So effectively, when you take the cross product, only this component would contribute to that, right? And this distance is a by 2. So a by 2 times the linear momentum is nothing but mv. Hopefully this step is clear. And in the second state, the angular momentum about the point O, we're assuming it's in pure rotation, right? So that will be nothing but the moment of inertia about point O times omega, right? So we have that. So let's solve that. So amv by 2 equals, I don't know how I switched colors suddenly. Okay, equals 2ma squared by 3 times omega. So m a cancel, and we get omega equals 3v by 4a. Isn't this interesting? When we conserve energy, we get one equation, and when we conserve angular momentum, we get another equation. So if you are confused like I am, I encourage you to pause the video now and think about this. Obviously, this is a single correct, single choice problem. So only one of these is correct. So it has to be one of these two. Before I give out the solution for this, I think this is a very interesting problem, and it really helps us think about a very important concept. But I just want to, think of another problem for a short while before we go back to the previous problem. So if we think about, let's say, a very common problem in linear momentum conservation, let's say there are two particles of mass m each. Let's say they are point masses, so not very small particles, and let's say this is at rest, and let's say this is moving with a speed v. All right, and let's say the collision happens. Okay, so I've given you the initial speeds, and I want you to find the final velocities of these two particles. So the common thing to do would say, okay, these are two particles, and if we consider them as the system, then there's no net external force on the system. So the momentum before collision, the linear momentum before collision, should be equal to the linear momentum after collision, because there's no external force on this system. Any force that they apply on each other is all internal, because we are analyzing, because we have defined A and B to be the system. Oops, sorry. So we have defined A plus B to be the system. Right? So P before should be equal to P after, and P before is nothing but MV. P after is MV1 or MVA plus MVB. Sorry, this thing is not. Yeah. Now, is this enough? Because we have two unknowns, VA and VB, and we have just one equation, right? So this is not enough to solve the problem. And this is where we need to know whether energy is being conserved or not. We know for sure momentum is conserved, but we cannot say energy is conserved for sure, because collisions can be of two types. Collisions can be elastic in the extreme case, or sorry, my pen isn't working properly, and inelastic. Okay, inelastic. Now, in an elastic collision, we know kinetic energy is conserved, whereas in an inelastic collision, we know the kinetic energy will not be conserved, right? That means some part of the energy of particle A is going to convert into sound or heat when it collides with particle B. So that means kinetic energy is not always conserved, right? And we have solved many problems like these. If the particles stick to each other, if it's an elastic collision, A will come to rest and B will move with speed v. And if it's an inelastic collision, A and B will stick together and move with speed v by 2 in this direction. And in that case, kinetic energy will not be conserved. So why am I saying all of this? This is a different problem. We were solving a different problem. But I just wanted to remind you that on what basis we can for sure, like the previous problem, we can like we conserve linear momentum here. We can definitely conserve angular momentum about the point O, because we know for sure there is no net torque about the point O. So this is definitely correct. Okay, this is correct for sure. But how do we know for sure that in this process of where it topples about the point O, none of the energy in this cube is converted into heat or sound? Because the problem doesn't tell us anything, right, about what kind of a collision or what kind of interaction is happening. So this is a very strong assumption to make, conserving energy, because we haven't been told. Unless the problem says it, we cannot really apply this equation. Whereas this is a more general assumption. Just like here, we can conserve linear momentum, but we don't know whether kinetic energy is conserved, that is whether it's an elastic collision, or kinetic energy is not conserved, whether it's an inelastic collision.